Alright, welcome to the next video in our SRP experiments, and this one's looking at the experiment to do with buoyancy or Archimedes' principle. And so you're going to have a variety of equipment. Now the equipment I've got here is larger, just so you can see it in the video, but we have a beaker here. You're going to have two beakers, probably maybe this size or this size. You're going to have a Newton spring balance to record the force or the weight of the object you're going to be measuring, and I'm using here a 1 kilogram mass. I've also got a set of electronic scales as well. So what is this experiment about? Well, it's about the upward thrust or the buoyant force that an object feels when it's immersed in water. And you would have done some research to find out what upward thrust means. So let's just have a look at this ball here. If we've got a ball in water, we know that it floats. Well, this particular one floats. Now, if you remember back to when we did the physics in terms of F equals ma, and we said that if you have an object on the ground, let's do it underneath the picture here. If you had an object underground, like that you have the pull of gravity going down. And that pull of gravity, so F is the force, G is gravity, and we put a little arrow over the top to represent that it's a vector quantity. Okay, you probably learned that when forces have a direction plus a magnitude, we call them vectors. And if not, check out the other videos that I've made on vectors. So we have the force of gravity pulling it down, and that's equal to its mass times the pull of gravity G. Now the thing is that we can also say that's the weight force. So your weight is your mass, how much stuff you're made of course, pulled down by the pull of gravity. And remember, you explored that concept, the difference between mass and weight, in the lessons that you did this year. So the weight force is equal to the mass times G. Now, since that this block is not going down through the floor, there must be an upward force to counteract that. Because remember Newton's third law, equal and opposite reactions. So in this instance here, there is an opposite force that goes upwards called the normal force. And so any object that is stationary has that. So for example, this block here, I'm holding it in, I should draw it on the bench, I guess. I've got that on the bench. And the block is being pulled down by gravity, but there's a normal force going upwards, called the normal force. Well, what about when objects are immersed in water? Well, here we have the ball in water now. So if we draw the ball in water, okay, we will have a downward force, the pull of gravity. But we've also got an upward force, and this time the upward force is not coming from a bench, it's coming from the water. And so we have an upward force. I'm just going to write BF for buoyant force. Another name is upthrust. So the buoyant force or upthrust is the force that's pushing upwards on this ball. So if I push the ball down, you can feel that there is a force pushing upwards. You all probably experience this when you go and swimming in a pool and you've got a nice big beach ball or something, you try and push that underwater and you can feel there's an upward force. That's the buoyant force. And the buoyant force acts on your body. I mean, you float on water, and the reason why you don't sink is because, of course, your density, but it's also due to this buoyant force acting on your body, okay? And if you ever get into scuba diving, the same thing's going to happen as well with the buoyant force. But let's just get back to this ball here. We know that there is a force pushing the ball upwards. Because if I do that, the ball gets pushed upwards. So we have this buoyant force. You have to measure that buoyant force. Now, how do we do that? Well, I'm glad you asked, because I'm about to show you. So what we do is we're going to look at our 1 kilogram block here. Now, if I get a Newton spring balance, this Newton spring balance is going to tell us how much gravity is pulling downwards on this block, and then we times it by the mass. So at the moment, it's hanging around 1,000 grams, or which is the same as 1 Newton, right? Or in this case, 10 newtons. All right, because 100 grams is 1 newton, so 1,000 grams is 10 newtons. So 10 newtons of force, right? So if we go to the board, we can say that the weight of the block in air is equal to its mass times the pull of gravity. The mass is 1,000 grams, which is 1 kilo, so let's write 1 kilo. And we times that by the pull of gravity, which is 9.8 meters per second squared. Now, we round it up a little bit in junior science. We usually say 10, okay, and that's why you've got 100 grams is approximately 1 Newton, okay. But here we've got 1 times 9.8, which is going to be 9.8 newtons of force. So that is the weight of the 1 kilogram mass. Let's see how the weight changes when we put it in the water. So here we go. It's still 1 kilogram or 1,000 grams. We put it in and we notice that the actual marker here moves upwards. It's less than 1,000 grams or less than the weight that we had before. So it's around about 840 grams, okay, or 8.4 newtons. So it's less. So this upward force, this upward buoyancy force is pushing the mass upwards, making its weight less than what it would be if it was hanging up in air. And so let's have a look here. We've got the buoyant force is what we're trying to calculate, but we just said that the weight in water was 8.4 newtons, okay? So therefore the buoyancy force must be the difference between those two. So the buoyancy force is the force in air, take away the force that we just measured, and so that the buoyancy force is 9.8, take away 8.4. Okay, and so what do we have? We have 1.4. So 1.4 newtons is the buoyant force. Right? That's the force pushing upwards. Now, can we measure that a different way? Well, in Archimedes' principle, it said that the buoyant force is equal to the mass of the water displaced. So let's do that. So we've got our electronic balance, and we'll just make sure it's nice and zeroed. Right? So we zero the balance. And we've got to measure how much water is displaced when we place the mass in. Now, to make it easier for me, I'm going to just tip some water into this medium-sized beaker. Okay, a bit more. All right. So what we're going to do here is I'm going to move this big beaker so the water is just about to escape, just about to go through the spout, right? And then what I'm going to do is I'm going to place the mass in there, and as the mass goes down, it's going to cause water to move into this one, which is displacing the water. So let's try that. Okay, getting it so the water's just on the lip, and then we put that in. And there it goes, the water's going in, right? I'm just doing this very quickly, right, so you can see. Of course, you'll take your time and be more accurate. And then we have some water in here that we've got to pour into another beaker so that we can see how much this water weighs, right? And if you do it accurately, it should weigh the exact amount that we calculated, all right? So let's do that. No, that's not right. 8.4, 9.4, 9.8. So it should be 140 grams. All right, so let's put our beaker there, and let's pour in how much water we collected. Whoops, let's do that again. Okay, so we've got to press the tare. Notice that we've got a weight of the beaker, so we press the tare button and that zeroes it back to 0. And so now anything we add to that, it's going to be measuring that. So let's measure the mass of the water. We put the water in from what we collected. And because we rushed, it's not that accurate. It says 155.86. 155.86. So we were expecting 140, because 1.4 newtons is 140 grams. So we should have 140 in there, but because I was rushing, and lifting the beaker up, we've got a bit of a difference there. But when you guys do it, take your time, repeat it multiple times to minimize those errors, and you should be more accurate. So we've just found that the amount of water, well, in this case it was 155.86, right? That's showing you that that water displaced is equal to the buoyant force, right? Now the buoyant force that we calculated was 1.4 because we rushed it. We didn't get it that accurately. So what you have to do in this investigation is calculate how the buoyant force changes when you have different liquids. So we did it with water, but maybe when you change the liquids, we're going to see, does the buoyant force differ? So if I had my same mass, right, I'm using the same mass, but I'm changing the liquids, does the buoyant force change depending upon what liquid you use, right? So that's what the investigation is. You know how to do it. You calculate it theoretically, right, which is what we did, right? And then you do it practically to determine if the amount of water displaced equals that force. And when you do it more accurately, it should, right? And then you do it for different liquids. And then you construct the graph to display your results. Now, if you remember, if you're not sure how to do the graphical analysis and how to construct a graph, you should by now, but if you're not, then make sure you look out the graphing video. All right, that's it for this experiment. Good luck.